Hi there. In this video we're going to talk about abstract groups and group presentations. We're going to go over the axioms of groups, talk about some examples of groups, then we'll look at permutations and group presentations. So what are the axioms of groups? These are the fundamental rules that groups must obey. A group is going to be a set with a product on it. It has a product and a special element that we're going to call E, which will be the identity. So these are going to obey the following rules. The identity times any element of the group will give us back that element of the group. So the identity does nothing to elements of the group. Given one order of multiplication, we can move those brackets around and still get the same product inside our group. And for every element of our group G, there's going to be an element G inverse, which undoes the element G. So when we multiply G times G inverse, that will produce the identity. Okay, so the sort of idea here is that inside a group, you can do G, and you can also undo it with G inverse. And for us, the major motivator for groups is the notion of a symmetry group. So in this course, all groups will be collections of symmetries of some object. Now let's get into some examples. A familiar example for Math 102 is the group of integers modulo n. So you take integers, you divide them out by n, and you look at the remainder. So you might remember an equation that looks something like this. 2 plus 2 in Math 102 can be 0. Right? If we're counting modulo 4, then 2 plus 2 is 4. That leaves a remainder of 0 on division by 4. So 2 plus 2 can be 0 if we're counting mod 4. So to put this in the context of groups, we've got a group element G star. Another group element G gives us the identity inside our group G. Right? So in this case, our group operation is the notion of addition. All right, let's have another look. One sort of geometric group is the group of rotations of a circle. So we're writing S1, the circle of one dimension, for the usual circle, and we can think of that as a group of rotations. Every point in a circle tells us how many degrees we need to rotate to get to that point. So we could have something like pi plus pi. Well, that's 180 plus 180. And if we rotate 180 and then 180 again, we get back to 360. So we've effectively rotated 360 degrees. And that's the same as not rotating at all. So we say that 180 product with 180 gives us the identity in G. Okay, so we can see that there's sort of a similarity between the integers modulo n and S1 somehow. S1 is an infinite group. It's got as many points as the circle has, so it's uncountable, but it still is very similar to the integers modulo n. Let's have a look at another group that we've seen. GL2R, the 2 by 2 invertible matrices with real entries. So this GL2 stands for general linear group. Okay, and this is because we study it in a linear algebra course, right? So these are all the linear transformations of the two-dimensional real vector space. So let's pick an element. We've got something like 0, 1, 1, 0. That has determinant -1, so it's definitely invertible. We'll multiply it by itself. So we're saying G star G. And now when we multiply this by itself, we get the 2 by 2 identity matrix in our group. Okay, so in the first two examples, the identity element looked like 0. And now in this example, the identity looks like 1, 0, 0, 1. So the identity of a group isn't always 0, but can look different ways in different groups. Now we're going to move on to one of the major groups in this course, the symmetric group, or the group of permutations. So what are permutations? Well, the symmetric group on n elements is all of the bijections from an n element set to itself. So we're going to say Sn is all of the functions from an n element set into itself. Right? So we can imagine taking, say, 5 objects and permuting them in some way, and that's creating a bijection from a set with 5 elements to itself. So the group product in this, take a moment, what would that be? We've got functions, they're bijections. If we multiply them, how should we multiply bijections? Well, we should compose them. If we've got 2 bijections, their composition is also going to be a bijection. Okay, so let's have a look at sort of the main reason why we use this theorem, or why we use this definition. Why is this symmetric group so important in this course? Every finite group is a subgroup of a symmetric group. So any finite collection of symmetries that we have lives inside some symmetric group. So that says that if we had just understood the symmetric group, we could understand every possible finite symmetry group that could come up. Now we're going to introduce some notation for the symmetric group. So a symmetry S can be written as a permutation P1, P2, Pn in the following way. So what we're going to do is we're going to write sort of a table of values where 1 gets sent to P1, 2 gets sent to P2, and n gets sent to Pn. So this is a very concise way of writing a table of values. We just write each entry right beside each other. And this is one way to write down a permutation. So this is a permutation such that P of k is the value of S applied to the number k. Okay, let's have a look at doing a calculation with this. So we want to calculate the product of 2 permutations, 1, 3, 2, and 2, 1, 3, in this kind of table of values notation. All right, so to calculate a product of permutations, we have to compose those permutations. To compose them, what we're going to do is we're going to see what happens when we feed in each number into this product. And if we know the value of the permutation on each number, then we can write down some notation that describes the permutation. Okay. So we're going to feed in the number 1. And just remember that in this course, when we write a group action, we write x, g. So here is our x, and here is our g. So we're going to look at what g does to x. So to figure out what g does to 1, we look in the first place of our permutation, and we see that this outputs 1. Okay, so we have outputted 1. Now, to see what the second permutation does, we're going to look again in the first place of our permutation, and we see that we output 2. Okay, so to summarize, when we plug in 1, we output 1. When we plug in 1, we output 2. Okay, let's have a look at how we would calculate what this permutation does to 2. So now this is our x, this is our g. To figure out what this does to 2, we look at the second position in the table of values, and we see that it should output a 3. So we get a 3 here. Now we're going to input this 3 into this permutation. And we see that we look in the third position, so we output 3. Now let's see what the permutation does to the value of 3. We take 3, look in the third position, so we output 2. Now we look at the second position, and we output 1. Okay, so let's put these pieces of information together. 1 gets sent to 2. 2 gets sent to 3. And 3 gets sent to 1. Okay, so there's our sort of table of values presentation of this permutation. So we get that the product of these is the permutation 2, 3, 1. This calculation's a little bit tricky, and I encourage you to go back and rewatch it if you're struggling to understand this concept. Now we're going to talk about a more geometric way of approaching permutations. We're going to talk about the notion of cycles. So to do so, we're going to sketch a permutation by drawing the set that it acts on, and seeing where every element gets mapped under this permutation. So the first element 1 gets sent to 3. The second element 2 gets sent to 2. The third element gets sent to 1. The fourth element gets sent to 5. And the fifth element gets sent to 4. Okay, so what we see is that this permutation sort of has 3 separate parts. It's got this collection, right, where 2 always gets sent back to itself. It's got these guys, 1 and 3, that get sent to each other. And then these guys, 5 and 4, that get sent to each other. Okay, so we can kind of think of this permutation as splitting up into a collection of cycles where 1 gets sent to 3, 3 gets sent to 1. 1 gets sent to 3, 3 gets sent to 1. 5 to 4, 4 to 5. 5 to 4, 4 to 5, right? It's sort of like a loop inside of this permutation. So we're going to introduce a definition to capture this notion. A cycle is a permutation that has each element get sent to the next one. So now we write this with round brackets, and we say that this permutation maps P1 to P2, P2 to P3, and ultimately maps Pk to P1, right? So the cycle closes up in the end. All right, so this is a permutation in Sn such that S of P1 gets sent to Pi plus 1 with indices counted modulo k, right? So we sort of wrap around at the end. Awesome. Now we're going to do a calculation with cycles. We want to calculate the product of the cycles 1, 3, 2 and 2, 1, 3 inside S3. So we're going to do the same thing as we did with the square brackets notation. We're going to look at what this permutation does to each element. So here we notice that 1 is sent to 3. So the output of acting with 1, 3, 2 on 1 will be 3. And here we're going to see where 3 goes. 3 is at the end of our cycle now, so we wrap around and output 2. Okay, let's see what this does to 2. We're going to take 2, feed it into this cycle. It outputs 1. So we get a 1 here. 1 gets sent to 3. So we see that we're outputting 3. Now we'll feed in 3. 3 gets sent to 2. We'll feed in 2. 2 gets sent to 1. So now we've got all of the information about this product. We know exactly what this product does to every element of the set 1, 2, 3. So let's have a look at what that looks like as a cycle. We see that 1 gets sent to 2. 2 gets sent to 3. And 3 gets sent to 1. Okay, so looking at it this way, we see that the product of these is going to be a cycle 1, 2, 3. Once again, this is some hard notation to handle, so I encourage you to go back and rewatch this section of the calculation. Okay, let's have a look at a geometric example. How will this actually come up for us in this course? Let's look at the group of symmetries of an equilateral triangle, and let's describe what these things are doing. So SA is a reflection across the line through A. So we take the triangle and we flip it over. And it has the effect of permuting B and C. Right? Those two endpoints get switched when we reflect across the line containing A. So we obtain that SA should be the cycle BC. Okay, what about SB now? SB is going to reflect across the line through B, so it will switch A and C, and we get that S of B is going to be the cycle AC. These symmetries, in fact, generate all the symmetries of the triangle. Reflecting in SA and reflecting in SB can be used to write every other symmetry of the triangle, all 6 of them. Let's have a look at what that looks like. To do that, we're going to need to introduce the notion of a group presentation. A group presentation is a concise way of writing down a group of symmetries. We write the group as A and R in little angle brackets, where this set A is the set of generators, and R is the set of relationships among those generators. Right? So it gives us a compact notation for writing down a group that may have finitely many elements, may have infinitely many elements. Let's look at an example. We can write Zn as being generated by G, satisfying the relationship that G to the n is equal to E. So this is going to have, if we want to write it as a list, it's going to be E, G, G squared, all the way up to G n minus 1. Okay, another way of writing this that you might have seen in Math 102 is to write this as a list of residues modulo n in the following way. What this group notation lets us do is it lets us perform calculations just using these relationships here. Right, so let's suppose that we're in Z3. In Z3, we have the relationship that G to the 3 is the identity. So we can calculate something like G to the 5 as being G to the 3 times G squared, which will be the identity times G squared. The identity times anything gives us the thing back, so we just get a G squared here. Right, so using this relationship, we can, in principle, compute any power of G. Right, so in that sense, the relationships capture the whole structure of the group by describing how the generators interact with each other. All right, let's look at a geometric example of this phenomenon. So we want to give a group presentation for the symmetries of the equilateral triangle. So as we mentioned, SA and SB generate the full group of symmetries. If we can reflect in SA and we can reflect in SB, then we can actually carry out all of the symmetries of this. How do we write the presentation, though? We notice that SA times SA, well, that's flipping and then flipping back, right? So that has to be the identity. Similarly, SB, SB, now we're reflecting in the line through B, and we're reflecting back. So that'll also be the identity. But how do these generators interact with each other? Right? What about SA times SB? How does that work? Well, let's pick a point, call it X, and we'll see where X goes under SA SB, right? So we apply SA first. We get over to here. So here's X. Here's X SA. Now we'll apply SB. So we'll reflect across B, and we wind up over here. Okay, so notice what this is doing. This is rotating our triangle about its center, and we can ask what the order of that rotation is. So the order of the rotation is going to be how many times it takes to come full circle. And we notice that if we apply this transformation 3 times, right, we're going to rotate a multiple of 2 pi. So we're going to get the identity. So these 3 relationships capture all of the structure of our group. And we can write down a group presentation using these generators. So we get that the symmetries of the triangle can be represented in the generators SA and SB, subject to the relation that SA squared is SB squared is SA SB cubed. And that all has to equal out to the identity. So what this has done is it's given us an algebraic way of describing the symmetries of the triangle in terms of generators that are geometrically meaningful. We can describe all the symmetries of the triangle just using these reflection symmetries. Thanks a lot for watching.